So we've learnt that the particle numbers, like we had 3% of a box, we know how much a box weighs, so occupies in volume, and we get basically 3% of 25 is 743 liters, 743 milliliters, I should say, or 0.743 liters. And just to complete it off, you normally go back to the question, you go, okay, what's the least amount of significant figures in the question? For instance, this is one significant figure, that's two significant figures. You go, all right, I cannot express my answer to be any more significant figures than the number that the least confident number that I've used. So this one's only one sig fig. I don't know if it's 0.5 4 and being rounded down to 0.5. And so there's uncertainty here. So I need to express my answer with that kind of vagueness and uncertainty. So technically I should say 0.7 liters, one sig fig. But it's not the focus. We're just learning about the mole concept. And so I set up here that we were using a visual tool and it doesn't quite work in real life. And you might have thought, well, how the hell do you get all these elements and compounds to be gases at room temperature and pressure? And obviously the vast majority of them are solids. And so this was a good visualization starting tool, and it theoretically works. But there is other methods to determine this. And so this is the one I start with, but there's also mass spectrometry, which you learn about in year 12, and that's module 8 of year 12, where they put everything into gas form and they measure out the mass of each element or whatever you're looking at. And you can use that to estimate, or based on the number of signals you get at each one, you can do an estimation of particle number. And you can also shoot x-rays, and based off how they bounce around and interfere with each other and come back and be detected, you can actually work out the spacing between particles. And if you know the density of particles, you can use that to estimate the number of particles present. So there's a number of different methods, and so you don't always have to have it in the box form that I was showing. And this like enables a complete picture where we can use all these numbers to estimate the number of particles in a mole. The accepted number is actually a huge number, which is 6.022 times 10 to the 23. It's called Avogadro's number, named after him. Avogadro did not figure it out. And that's a whole story in itself, where basically they use two numbers from two famous experiments, which physics explores. And essentially they figured out the charge of a mole of electrons, and then they divided by the charge of a single electron, and that gave them the number of electrons, which is also the number of atoms if one electron is coming off one atom or one particle. And so, this is its own little story, but we're not going into it. And so the assumption here is these boxes at a certain temperature and pressure, they all contain 6.022 times 10 to the 23 particles, of O2 or lead or sulfur. And now the assumptions are just digging into it a bit more. So we're assuming that they're all got the same number of particles. That's a good assumption. Those particles occupy negligible volume relative to the box. Okay, so this is going to lead into our next concept, which is gas laws. And we're also assuming that these particles are not attracted to each other. Okay, and that kind of is true if it's really high temperatures, and not quite true if it's low temperatures, and also true if it's low pressures, but not quite true if it's high pressures. And I had asked you to firstly visualize like all these particles as the same size, which is not a bad assumption and not a great starting point. But just to be more clear, it does actually account for the different size particles because they're occupying such less volume relative to the box. You can kind of have the same number of particles and have them as different size and still have all this to be true. Okay. So a lot going on here. Recap is that you've got to accept that volume in gas is proportional to particles. 1 liter will have the same number of particles as 1 liter of another substance, for instance. And then you use that principle to get differences in mass, and that's way more useful. And you basically then use mass as a ratio of all these accepted values, so these molar masses or even these molar volumes, and you're able to work out the number of particles present and use the balance equation. A word that I haven't introduced yet is stoichiometry. So the ratio that things react is called stoichiometry. It's got a very hard spelling. So the 3 to 2 to 2 to 3 to 3 ratio, you would call that stoichiometry. And so you use the stoichiometry and the mole concept, and you can figure out how much do you produce or need and all those kind of things. We're about to move on to gas laws. So stay tuned. Gas laws are kind of a bit easier. If you can get the mole concept, I think the rest of the course, including year 12, becomes about the same level to grasp. So if you're picking up the mole concept easy, this is the course for you. It is not something that you can't just do one question and be like, oh, I know it. It takes a lot of repetition to get to these questions. Some of them can be quite hard, FYI.